All right, so combining functions. We're going to look at kind of two big ideas. One is function arithmetic, which is what we're going to mainly focus on today. And then function composition, we'll spend most of Thursday on that. So first, arithmetic, though. The idea here is that, I know something about two functions called f and g. So those are given or known somehow, and we're going to be combining them. So first, maybe a real quick recap on function notation stuff, since we're going to lean on that pretty hard. Hopefully we're getting familiar with this from homework and everything that we've been doing over the last couple of weeks. But function notation is how we write down or how we express a relationship between two things, call them x and y, right? So when we write y equals f of x, and that's f of x, what we mean is, okay, there's some relationship between x and y and some specific way that they're tied together. And I'm going to name that relationship f just because I don't want to have to keep writing it down or saying it in English or whatever, right? So maybe, to get from x to y, you take x and you multiply it by 3 and then you subtract 5, right? I don't want to have to keep saying that. I don't want to have to keep writing that formula down. So I name it f instead, right? But then when I name, actually, let me back up. I don't remember what I said, add or subtract or whatever, it doesn't matter. But when I write that formula down, for it to really be like a thing that does something, I have to have some place to plug in a variable, right? We usually call that x. That's the independent variable or the thing that works like the input, right? But I need a place to put it. So the kind of default thing is to say, well, okay, there's some placeholder, but let's call it x, right? I just need it to not be a number because numbers have like a specific meaning, right? So I need some symbol for it. X works as well as anything else. So let's go with that. But it doesn't mean anything different than if I wrote it with a T or this little smiley face thing. Like, it doesn't matter. It's just a placeholder for something else, right? And the way the function works is, okay, I say find f of 2, and you say, okay, f of 2 means anywhere there was this thing, whatever it was, I'm going to replace that with 2. And then it just turns into an arithmetic problem, right? Then it's something you could have done when you were and now it's like an elementary school problem, right? Just evaluating this. So this thing is just a placeholder. That part's important. We're going to, lean on that a little bit. And f, I don't know why I deleted that. Someone might still want that. F right here, that's just the name of the function, right? Calling it g or h or whatever else would be just fine. We probably want to avoid x and y because I've already kind of assigned a different meaning to them. But otherwise, I could use whatever I want. We just default to calling it f because function starts with f and we're kind of lame like that, right? Okay, so that's the name of the thing. So what we're doing when we talk about function arithmetic, don't worry about all of these, just look at one at a time. What we're doing here is defining a new function, right? So pretend I know something about a function called f. I know something about a function called g, even though I haven't written those here. They're things I already have, right? F and g. What we're doing here is defining a new function. We're going to write it in terms of x, so that's going to be our symbol or a placeholder still. But what are we naming this new function?
F of x plus g of x.
The thing that we're naming it is f plus g of x. And if there's any, justice at all in the way that we're doing this or reason for doing it, it's that what it ought to do is take f and g and add them together, right? So f plus g, this new function that we're defining, is just f plus g. I know that difference is kind of subtle, but it shows you exactly what the thing does and also gives us a way to do it, right? So if I have a function called f, say f of x is x plus 1, and g of x is, I don't know, 2x minus 3. Okay, I know what f does. F takes something and adds 1 to it, right? That's what this, is telling me to do. Anything you give it as input, add 1 to that, that's what the function does. G takes something, multiplies by 2, and then subtracts 3. Again, that's like what this is telling me, right? It's how to find y's from x's. If I know those already, and I wanted to find a new thing called f plus g, well, all I have to do, thankfully, is take f and take g and add them together. And that's the thing I know how to do, right? That's just f plus g. And then we do the arithmetic or do the algebra to combine stuff. So x plus 2x would be 3x, 1 plus negative 3 would be minus 2. That's a new function whose name is f plus g, because what it does is take f and g and add them together. Okay. I know it feels like I'm making a big deal out of maybe not a big deal, but it's a little subtle, and understanding the kind of way the notation works and what's actually going on here, I think is going to help us moving forward too. So that's why I'm making a big deal about it. What's f minus g of x then? Same thing, only subtract instead. And the others, well, fg written right up next to each other like that means multiplication. So it's f and g, and we're multiplying. So f times g, or fg, is f times g, and f over g would be division. Okay, so if I have two functions, and they don't have to be different, right? It could be the same function. You could have f plus f or g plus g or whatever. That's normal, that's allowed. If I have two functions and I want to combine them using arithmetic, this is good news, right? This just means that all you do is the arithmetic, like it is what it looks like it ought to be, right? That's good. It's not some weird like hidden meaning thing. F plus g means we'll take f and take g and add them together. So this first example here, now I am actually giving you a function called f and a function called g, right? Take f of x to be x squared plus 3. Take g of x to be negative x plus 2. I want you to do a couple things with those. Combine them, right? So there's 4 parts here. We're going to do all 4 arithmetic operations. Combine them and simplify, right? So add, subtract, multiply, divide, and simplify what you can simplify. And then the second part to that, once you've done that, once you've found f plus g of x with these two specific functions, I want you to think about its domain and plug in -2. Plug in -2 and evaluate, if you can, if that makes sense, if that's in the domain, if that works. So let's take, 10 minutes or so. You guys work through those. Right there is probably not going to be enough room to do it, but work through those, talk to people around you, ask questions as they come up, and then we'll talk about them together in a minute. All right, so we walk me through the difference, f minus g, part B.
Right out the f squared plus 3
Mm-hmm.
minus negative x plus 2.
Yep. So it's f minus g, right? And what I know about f is that f is equal to, or the same as, or replaceable by, or interchangeable with, or whatever, where you see one, you can put the other one, x squared plus 3. So f minus g, I can replace f with x squared plus 3. Right? That takes it from, okay, some abstract, concept of what this function f means to this specific one that I know how to do algebra with. Right? That's kind of the point of doing that replacement. Minus, same idea for g. Okay. Now, how do we actually combine them?
Well, negative x and x squared, I put negative x squared.
Say that one more time.
You do both the x's, you combine those.
These two?
Yes.
Okay, so how are we combining things here?
Subtract.
Subtracting. Okay, we're subtracting. When you add or subtract, you want to combine like terms. What does it mean for terms to be alike? They got to be the same kind of thing. When I say kind of thing like that, or like term, same symbol, of course, right? So x's and whatever, but also same degree or power or number of them there, right? So x squared means x times x. The other one is just x itself, right? So if you want to think about this in like number terms, well, never mind. That's probably a bad example. These aren't the same kind of thing, right? Because they represent different numbers of that variable, if you want. So since those aren't like terms, we're not going to combine them. So when we subtract, this is the only place where I get an x squared term. Goodness.
Squared minus x plus 5.
Yeah, and then,
Or I'm sorry, plus 1.
since we're subtracting that whole thing, this is why I threw that set of parentheses there, minus negative x, right? If you subtract a negative, then you get positive, and then minus 2. And then again, we're just looking for, so that's basically breaking down the subtraction, right? This set of parentheses isn't really actually doing anything. We're subtracting this whole thing, so I carry that negative through, these signs change. Now look for like terms to combine. This is the only square term. So that's that taken care of. Plus x here, that's the only linear term. And then 3 minus 2 would be, so plus 1. Okay, so that's the actual operation done, the subtraction, and then everything combined and sort of cleaned up and simplified, and that's as far sort of as compact as I can make that thing. Okay, now what about the domain? So that's the other thing I asked you for here, the domain of the new function. Why?
Because it is an x squared value, and that would mean it would go, that would mean it would be one of the U-shaped.
Yep.
terms.
Yeah, good. So this function that we've ended up with, x squared plus x plus 1. We can't quite do all the stuff we did last week and break down like it's x squared, but moved, exactly like this because of this, right? The plus 1 I can make some sense of, but this kind of throws things off a little bit, that x term in the middle. But looking at the highest order, the highest power term, still tells us what kind of thing it is, right? What family of functions it belongs to. This is going to be a square function, which means it's going to be, parabola is the fancy word for the graph, but it's going to be a parabola somewhere. I don't know where exactly quite yet. We don't quite have all those tools yet, but I know how these things are defined, right? I know how these things work. So the domain there is everything, all real numbers, negative infinity to infinity. If you look at the original functions that we started with, f, this is x squared plus 3. That one I can do the transformations, right? It's x squared, but moved up 3. That's defined everywhere. This is just a straight line. It's got negative slope and y-intercept too, but that's defined everywhere also. So I took these two things that are defined from negative infinity to infinity, I subtracted them, and we get another thing that's also defined everywhere. I'll circle back to that idea in a minute. Okay, so is everybody okay with like just the mechanics of how we combine those? Like the, working through the algebra to actually do the combination? Yeah. And let's also talk about multiplication real quick. Wait, work smarter, not harder. Okay, so I'm going to do the multiplication, part C. FG again means F times G, so we're multiplying here. So what do we need to do to actually multiply those two things? X squared plus 3, as a quantity, as a whole piece, times quantity, negative x plus 2.
Is that where you distribute?
Yeah. Distribute what?
X squared to negative x and then 3 to negative x.
Yep. So you distribute everything, right? FOIL is one, mnemonic for that. If you want to do the sort of like Punnett square type thing where you write it out as x squared and plus 3 and negative x and plus 2, and then you do all the multiplications, right? I usually just draw arrows like that, but you're multiplying a quantity by a quantity. Everything here should hit everything here, right? Okay, so x squared times negative x. And now, since we're multiplying, we don't care about, like or unlike or whatever, right? We just do the multiplication. So x squared times negative x. Negative x. And now there's 2 from the square and then 1 more, so 3 of them, right? So it's negative x cubed. The square is x times x and then times another one, right? So cubed. And then x squared times the other piece from the sort of second term there, 2x squared. And then do the same thing with 3, right? Distribute it through to both pieces. So 3 times negative x and 3 times 2 plus 6. And looking at that, there are no like terms, right? These all have different powers on them. So there's nothing to combine. That's it. What about the domain? Again, like this function looks even more complicated, right? There's a bunch of stuff going on, but what kind of thing is it? It's a cubic. These lower order terms aren't going to change that. Those are going to, change the shape a little bit, move it around maybe. Looks like there's some kind of reflection here. I, again, don't have the tools right now to say specifically exactly what that's going to look like, but it is a cubic function. So it's going to behave like x cubed does. And where is x cubed defined? Everywhere. So far, thinking back to all the functions that we looked at last week and did all the transformations with and stuff, there's only one thing that's not defined over the whole real line, and that was the square root, right? The square root function is defined only from 0 to infinity. Why was that? If you give it an x value, what you're going to do is take the square root of that number, right? So what happens over here that's a problem? What happens if you try to take the square root of -2? You can't, right? It's not a real number anyway, right? Calculator will, bark some kind of error message at you or whatever, but this is not a real number. Because it's not a real number, and that's all we care about when we're talking about graphing and domains and stuff like that. The function is not defined there. The same thing would be true for any negative number. That's why the domain looks like this, right? Now, if you take a square root function and start moving it around, like, what does that +3 do? Takes our square root function and moves it to the left 3. Well, the domain moves with that then, right? So the domain here would be, rather than 0 to infinity, -3 to infinity. Okay, so far, pretty much what we know about domain and what we should be on the lookout for is that if you got a place where you would end up with a negative number under a square root, that's going to be a problem, right? So we got to look out for that kind of thing. Squares, cubes, linear stuff, absolute value, those are all defined everywhere. So they're a little easier to work with. We're about to add something into the mix though, and that's what happens if we look at f divided by g. So, oops. F over g. Well, f over g, again, would just be f over g, right? So it's f over g, x squared plus 3, negative x plus 2. That's just f divided by g, right? Just replacing what we know about f and what we know about g. And what's the thing you're probably, I don't know, wondering or concerned about maybe? What do we do with that, right? Addition, subtraction, multiplication, you kind of know like where to go, right? How to simplify that, right? Just do the thing, right? Clean it up. Division's harder. And division, you probably haven't done polynomial division before that would give us a way to clean this up. So the good news is we don't have to do anything because there's not really a good way to clean things up. That thing, is what it is. We will later on, I don't know, a couple months, maybe 6 weeks from now, something. We will talk about how to do polynomial division to, give us a way to sort of express that kind of thing differently. We're not worried about it right now. It doesn't always work out very nicely, so this thing, we're just going to leave it as it is. We're not going to worry about simplifying that at all. That's f over g. But we do still need to think about the domain. Addition, subtraction, and multiplication, those are what I like to think of as nice operations because they don't add in new weird stuff. Division is not. Division's, division's always kind of a pain, right? That's why everybody's like a little bit afraid of fractions, right? Because it's division. So division's kind of a hassle a little bit. These two functions on their own were perfectly nice. They're defined everywhere. But when we take one and divide by the other, all of a sudden things are different. And the reason that they're different is this. If you have, so this is just a quick division review, I guess. What's the way you first kind of learn about or, introduced to division? Okay, even before that, like just the concept of like 4 divided by 2. Yeah, maybe multiplication. Even before that, like you're 3 years old and you have to share with your little sister or whatever, right? Just sharing, right? Just equal partitioning. You've got 4 cookies and you've got 2 friends, 4 cookies to give away, I guess. I don't know. You've already taken your share out or something, but 4 cookies and 2 friends, how much does everybody get? 2, right? Okay. And then everybody's happy. It's fair, right? Well, what if you have not 4 cookies. What if you have no cookies and 2 friends? Nobody gets anything, but like at least you still have your friends, right? Well, probably not. Okay, maybe don't tell them that you're like, don't make a big deal about the fact that you're not sharing cookies with them, but you know, nobody gets anything though, right? What if you have 4 cookies and no friends? And a deathly allergy to whatever's in the cookies or something. It's not a perfect analogy, right? But like here, it's still okay because you still have your friends. But 4 cookies and no friends, that's bad, right? We're sad about that. Again, this is a situation in which you are unable to eat the cookies. I understand that that's, you know, runs counter to some things, but division by 0 is a problem, right? This is saying how many times does 2 go into 4? Well, twice, right? How many times does 2 go into 0? None. How many times does 0 go into 4? What does that even mean, right? How do I break 4 up into 0-sized pieces? Like, I don't know. There's infinity of them, maybe, I guess. I don't like what this operation is undefined, right? This doesn't exist. There's no way to do that, which is why we're sad about it. What does that have to do with talking about the domain here? Well, X takes on a whole bunch of different values, right? So for example, what if I took this thing and said, hey, what if I took that function and asked you to evaluate it for when X is 2? So plug 2 in, right? Anywhere there's an X, replace it with a 2, and what do you get? 7 on the top, put it in the denominator. -2 plus 2 is 0. And 7 divided by 0 is not a thing, right? It's undefined. Zero divided by 7 would be 0. 7 divided by 0, anything divided by 0 is undefined because this means, you know, figure out how many of these go into that. Well, like I can't, right? I can't make 7 up out of zeros. I can keep throwing zeros into the pile all day long and never get to 7, right? So this is undefined. This is bad. That's why I keep making it a frowny face. That's undefined. Well, that means that the function would also need to be undefined. And a function being undefined literally means that point is not in its domain because the domain is where it is defined, right? Is there anywhere else that that would happen? So 2 is a problem.
Is 2 a problem with division? No. Divide something in half pretty easily.
Right. Sorry. I mean, X equals 2 for this function is undefined, right? I mean, like X can't be 2 because if X is 2, then I get 0 in the denominator. That's the only place that would happen, right? X can be 1, it can be 5, it can be 47, right? Anything else is fine. It's just that one place where the denominator would be 0. So the domain then is we've got the x-axis, right? Everything. So something out here, you know, -17 or whatever, that's fine. 2 is the problem. But anything else is okay. How can we write everything except for 2? How do you write everything in, you know, interval notation? Negative infinity
So what you do
to infinity.
Actually, for this one,
Mhm.
the domain, you do negative infinity to 2, and then the u, and then 2 to infinity.
Okay, and what do we do with the 2's for the endpoints?
You block them off. You put them,
We block them off. We don't quite want to include them, right? 1.99999 forever is okay, but 2 is not. So how do we do an open interval or say like up to but not including? Parentheses. Bracket would mean include the thing, But I can't include the thing because if I do, I get something that doesn't make sense, right? I get something that's undefined. So that is everything except 2, that's this written out as an interval, right? That's where that would be defined. So domain stuff. Domain things to watch for, I guess. I don't know. The one that we kind of talked about and looked at last week. No negatives under a square root. And I mean exactly what we talked about a few minutes ago, that whole radicand can't end up being negative, right? It doesn't mean that you can't have like x minus 1. It means that you need to think about what that does, right? And how that affects things. And can't divide by, so in the denominator, 0. There are a couple of things that we'll add to this list as we go through the semester, but it's never going to be much longer than about, I think by the time the final rolls around, we're going to have like 4 things maybe that we need to be careful about and be aware of if we're thinking a domain of a function. The radicand for a square root or an even root can't be negative, so stuff underneath, and the denominator of a fraction or the divisor can't be 0. So if we're combining functions using arithmetic and then finding their domain, if the functions that we started with are nice, right? Squares, cubes, linear, whatever, then add, subtract, and multiply are not going to change that, right? But division, because you put 1 in the denominator, right? That might affect things. Not always, but we need to be aware of it. Okay? Okay. Everybody good so far? Anybody have any questions about anything? So that's all kind of how you do function arithmetic symbolically, right? Algebraically with the equations. You add them together, you subtract, you multiply, you divide, you do whatever you need to do to simplify. What if we want to do the same thing, but from a graph? So here's a graph. It's got a function called f on it. It's got a function called g. We want to find f plus g of 0, for example. What do we need to be able to do to answer that?
So that would be, you said x equals 0.
Yep.
And then what that is, and you get 0 plus 2 equals 2.
That's an x value, right?
Yes.
Okay. So what's my answer to part A going to be? Like, what kind of a thing is it going to be? What's the answer going to look like?
Find where one of the values intersects with 0.
Yeah.
So you look at that graph, it says, which one is that? That's
Don't worry about the like specifics just yet.
Yeah.
If I give you an x, then your answer is going to be the y that goes with it, right? Okay. So given an x, your answer is going to be a y. My answer is just going to be a number then, right? It's going to be 5 or 17 or I don't know yet, but it's just going to be some number. The y value that goes with f plus g. So I need to find what f is. I need to find what g is, and then I need to add them together, right?
Okay.
To put it like sort of most simply, somebody last class, just said, we just need to be able to read the graph. That's all we need to do. We don't need to figure out, what this function is. Okay, it's a line and its slope is 2 and whatever, and like write it down. I don't need to do all that. All I need to do is read the graph. Go to x equals 0. Where is x equals 0? It's right here. Okay, so go to x equals 0. And this is all the places where x equals 0, right? So all I'm going to look at is that highlighted, little strip there where x is 0. I'm going to figure out what the two functions do because I need f and I need g. So I'm going to find f and g there, and then I'm going to add them together because it says add them together, right? Again, just looking at, part A here. Okay, so what is f when x is 0? Yikes. What is f when x is 0? 0. There it is, right? That point is the one I care about. 0, 0. The x value 0 is what I gave you. So what you need to get back from that is the y value. They happen to be the same, but whatever. That's f of 0. All right, I'm just taking this y value and placing it there. Okay, what's g of 0? When x is 0, g is this graph. So g of 0 is 2. So then again, I'm going to take the y value here and put it where g of 0 ought to go. And 0 plus 2 is 2, and that's our answer. That's it. So plus because it said f plus g, right? And then just looking up at the one x value, looking up both function values, and then just doing that, right? So y'all tell me about f minus g of -1. Find -1. There it is. What's f there? -2. The problem's telling me to subtract, so I'm going to subtract. What's g? 1. And -2 minus 1 would be -3. Yeah. Just reading the graph, right? Reading the graph and doing, the operation that it says to do. All right, so y'all take a second, do the other two there. Oops. Yeah. So for C, I get 2. F, when x is 1, f is 2, g is 1, 2 times 1 is 2. And then for D, -2. So when x is 2, f is 4, and g is -2, and 4 by -2 is -2. Are you happy with that? Okay, that's function arithmetic. And notice, again, I'm just going to make a big deal about this for a second. I did not need to try to figure out what these functions were, right? I didn't need to work out any algebra. I didn't need to, look at G and say, oh, I recognize that shape. That's a square, but it's upside down. So there's a reflection and it's up 2. So that must be, G is -x² plus 2. Like, I don't need to go through all that and then combine and then plug in and do all that, right? That turns it from a problem that I could do, 4 parts here in, now that you've done it once, you can probably do all of that in a minute or something, right? Into a 5-minute problem where there's a bunch of room to make little mistakes and whatever, because you're doing a whole bunch of extra work that we don't really need, right? Okay, so I'm just gonna point that out as we're going by. Tomorrow, well, not tomorrow, but Thursday, we're gonna talk about function composition. Composition is gonna look a little different because of, again, the terminology and formality and stuff, but it's an idea that you're already familiar with. And as an example to show that to you, think about this example number 3, between now and Thursday. There's a pair of shoes that you would like to buy that is regularly $70. They're on sale for 25% off. You have a coupon for an additional $10 off. There's no fine print about discounts being stacked or when you may use the coupon or whatever. Somebody pointed that out last hour. They're like, whoa, buddy, you can't use that coupon today. That's not happening, right? So 25% off, then an additional $10 off. How much are they going to cost? How do you find it? Does it matter that we think about the order in that way? Think through this for next time, and we will pick up there on Thursday. All right. All right. Y'all have a good day. I will see you Thursday.